Hello friends and dear students, today we are going to do an activity on Pythagoras theorem with the help of Bhaskara method. Pythagoras theorem states that the square of length of hypotenuse is equal to square of length of perpendicular plus square of length of base. To do this in activity, the material required are scissor, scale, glue, pencil, color pen and 4 replica of right angle triangle. These 4 replica are congruent to each other. Now, let us name this right angle triangle as A, B, C and their respective distances of the hypotenuse is C, A, B. Now, with the help of these 4 replica, we will make a square with where we will consider the hypotenuse at the side of the square. Now, we can see that this is a square where we have already made it. Now, we have seen that we have a square. Let us name this square as P, Q, R, S. Here we have seen that inside the square there is a one more square where the length is A minus B unit. Now, area of square PQRS is equal to the area of square of side A minus B units added to the area of 4 identical right angle triangles of sides A, B and C units. Now, the area of square PQRS is C square, which is equal to 4 times area of right angle triangle, this is which is equal to half of AB plus A minus B whole square. After simplifications, we will get this is equal to C square is equal to S square plus B square, which verifies the Pythagoras theorem, that is hypotenuse square is equal to perpendicular square plus base squares. After simplifications, we have found that length of hypotenuse square is equal to length of perpendicular square plus length of base square. Dear students, you can verify this theorem cutting different replica of right angle triangle of your convenient size and you will get the
With the help of an activity, it is easy to visualize geometrical aspects. Hello students, today we are going to verify basic proportionality theorem, also known as Thales theorem, with the help of an activity. To demonstrate this activity, we have made an assembled model in which 2 graduated scales are attached parallelly to each other to a wooden base, and between these 2 graduated scales, a scale is attached which is parallel to the base, supported by these 2 pulleys. Now students, what do you mean by basic proportionality theorem? Basic proportionality theorem states that if a line L is parallel to any one side of a triangle to intersect the other 2 sides of a triangle at distinct point, then the other 2 sides are divided in the same ratio. We are going to verify this basic proportionality theorem in 4 cases, when we have a scalene triangle, a right angle triangle, an isosceles triangle and an equilateral triangle. So, let us take case 1, when we have a scalene triangle. Now, you can see that this is a scalene triangle A, B, C, and this scale which is representing the line L is parallel to the side BC of this triangle A, B and C. Let us adjust the scale at some position. Now you can see that this line is parallel to the side BC and intersecting the other two sides of the triangle ABC, where it is intersecting the other two sides of the triangle AB at say E and AC at F. Now we have to see whether it AE by EB, AF by FC are same or not. Now on measuring AE, EB, AF and FC, we can see that. On measuring AE, we can see that AE is how many units? 4 units. EB is 8 units. Similarly, on measuring AF, we can see it comes out to be 6 units. It was AF, it is 6 units, and FC is 12 units. Now on calculating, as we can see, AE by EB is equal to 4 by 8, which is equal to 1 by 2. AF by FC is equal to 6 by 12, which is again coming out to be 1 by 2. This shows that AE by EB is equal to AF by FC, which shows that the other two sides are divided in the same ratio. Now, let us take for some other position, say suppose here. Now, this again you can see in this that this scale which is representing the line L parallel to BC and intersecting the other two sides, that is AB, say at some position say G, and AC at say suppose H. Now you can see again on measuring AG, GB, AH and HC that whether the two sides are divided in the same ratio or not. On measuring AG, we can see that AG is coming out to be 8.4 units and GB is 3.6 units. Similarly, AH is coming out to be 12.6 units and HC is 5.4 units. Again, by mathematical manipulation, we can see that AG by GB is 8.4 upon 3.6, which is coming out to be 7 by 3, and AH by HC is 12.6 upon 5.4, which is again coming out to be 7 by 3, which shows that the other two sides are divided in the same ratio. Now let us take for the another case. Let us take for the right angle triangle. This is a right angle triangle PQR, right angled at Q. Let us take some position, say suppose at this point. Again you can see in this triangle PQR, this line L is parallel to QR and intersecting PR, say suppose at, let us write it as D, and PQ at, say suppose E. Now on measuring PD, DR, PE and EQ, we can see whether the two sides are divided in the same ratio or not. So on measuring PD, we can see that it is how much? 6 units, and DR is how much? 18 units. Similarly, on measuring PE, we can see that it is 5 units and EQ is 15 units. Now, by mathematical manipulation, we can see that PD by dr is 6 by 18, which is coming out to be 1 by 3, and PE by EQ is 5 by 15, which is again coming out to be 1 by 3, which again shows that the other two sides are divided in the same ratio. Now, you can repeat this process by putting the scale up and down and verify yourself that whether the corresponding ratios are equal or not. Now, let us take the third case for isosceles triangle. So, you can see that this is an isosceles triangle STU. Let us adjust at some position, say suppose here. Since it is isosceles triangle, so this you can see that ST and SU are equal. This line L is again parallel to TU and intersecting the other two sides of a triangle STU at, say suppose again G and H, where ST is intersect, or we can say where line is intersecting ST at G and line L is intersecting SU at H. Again we can see that on measuring, SG is how much? 10 units and GT is, we can see 13 units. SH is also 10 units and HU is also 13 units. So, it is clear that the ratio of SG by GT is 10 by 13 and also the ratio of SH by HU is 10 by 13, which again shows that the other two sides are divided in the same ratio. Let us take the fourth case, where our triangle is an equilateral triangle. Now, you can see that this is an equilateral triangle with all the three sides are equal, W, X, Y. And again, this line L is parallel to XY, intersecting WX and WY at different points, or we can say distinct points. So, again by pulling the scale up and down, take the different position and verify yourself whether the corresponding ratios are equal or not. This is how we have shown that whenever a line L is parallel to any one side of a triangle, intersecting the other two sides at distinct points, then the other two sides are divided in the same ratio. This verifies our basic.
Hello children, in mathematics, geometry plays a vital role. In geometry, we do come across many theorems and results. For better understanding and more visualization, we do perform some activities in our math laboratory. Today, we shall perform an activity which verify the relationship between areas of similar triangles and their corresponding sides. To establish the relation, we take a triangle of our convenient sides and some replicas of this triangle. To establish the relation, we arrange these triangles in this manner. Now, we have triangle A, B, C and triangle D, E, F. Now, I place angle A over angle D, very clear that these two are equal, and I place angle B over angle E and these two are equal, and I place angle C over angle F, these two are equal. In these two triangles, these three angles are equal. By AAA similarity, these two triangles are similar triangles. Now, we shall see about these their areas. In the triangular region, DEF is covered by the replicas of the triangle ABC. It is very clear that the triangle DEF is 4 times of the triangle ABC. So, we can write that area of triangle DEF is equal to 4 times of area of triangle ABC. Now, the ratio of their areas is area of triangle ABC is to area of triangle DEF is equal to 1:4. Now, we shall see about their corresponding sides. Now, I shall place this AB over DE, it is 2 times, and we shall place BC over EF, it is 2 times, and we shall place AC over DF, it is 2 times. So, the ratio of their corresponding sides is 1:2. Now, ratio of square of their corresponding sides is equal to 1 square is to 2 square is equal to 1:4. From the equation 1 and equation 2, it is very clear that the ratio of area of their similar triangles is equal to square of the ratio of their corresponding sides. Now, we shall perform this activity with some more similar triangles. For that, we arrange the triangles like this. Now, we shall see their corresponding sides. Here we have triangle ABC and triangle PQR. Now, we place AB over PQ, it is exactly 3 times. Now, we place BC over QR, it is exactly 3 times. Now, we place AC over PR, it is exactly 3 times. So, the ratio of their corresponding sides is 1:3. Square of ratios of their corresponding sides is equal to 1 square is to 3 square is equal to 1:9. From equation 3 and 4, it is clear that the ratio of areas of these two triangles is equal to ratio of square of their corresponding sides. Children, by taking more similar triangles, you can verify this result.
In my childhood, I have played with this toy a lot. Basically, there's this doll. If you open this, you'll find another doll. Opening that, you'll find another one inside. Well, you too might have come across this toy or might have played with this toy. And if you haven't, let's take a look. So what you see is that all these dolls actually look exactly the same as the other. The only difference is the size. So the difference is only in the size, and in geometry we use the term similar to show that the only difference is the difference in size and the shape is exactly the same. Also we know that if you go to a photographer, then from the same negative, a photographer can give you a photograph of any size. So be it a passport size photo or a stamp size photo, what you see is that the photo is exactly the same. What has changed is just the size of the image. So these two again can be said to be similar because the only difference is difference in size. So far we've studied about congruent images, which means that they have exactly the same shape and the size. And we use this symbol to represent congruent. This two lines at the bottom show same size, whereas this inverted S shows same shape. So this was congruent. Now what we'll study is similar. So similar means same shape, not necessarily the same size. And since same shape is indicated by an inverted S, what we get is just an inverted S. So these two images here, you can see, are same in shape, but the difference is the size, and hence I can say that they are similar. Now let us try to apply this in geometry. So we have these different similar figures. Similar figures, only difference is difference in size. Look at these line segments here. All look exactly of the same shape. Only difference is difference in size. Now the square is also of the same shape. The difference is the size. So only the side is changing, and hence the shape of this shape is not changing. Only the size is changing with the change in the side. Again, different circles are also can be said to be similar because what is changing is just the radius. The shape is not changing. All are circular. So now I have different line segments, I have squares also, I have circles also which are similar. Can I say that triangles are also similar? Let us look. Let us see that we have these two triangles here. Can I say that they are similar now? So when can I say that they are similar? If they have the same shape. Now do you think that they have the same shape? Let me try moving this a bit and see whether they look of the same shape. It doesn't seem like. I also know that similar objects, if things are similar, that I can decrease the size. Size is not an issue. The shape is the only thing that has to be the same. So let me decrease the size. So I'm not changing the shape, but just the size. And they both still don't look of the same shape. So since the shape is not the same, I can say that they are not similar. So now these two triangles are not similar. So when can I have similar triangles? I know I get similar things when one is the smaller or larger image of the other. So only the difference is difference in size. So what I do is I make such triangles. So I have this triangle here. I make another triangle, a larger triangle than this, such that the shape remains the same. Now in both these triangles, what you can see is that the shape is the same of both these triangles. The outer triangle that is outside is actually larger than the triangle inside. The only difference is the difference in the size. Shape is the same, so I can say that they two are similar. Now, I make another triangle, which is larger than this triangle also. Again, you can see that you can put one inside the other, shape being the same. So the shape of all these three are the same, only difference is the size. Also you can see that the outermost triangle looks like a projection of the innermost triangle. So outermost triangle is also in a way larger, or the only difference in the outermost and the innermost triangle is the difference in size. The shape is the same. The size is changing. It has increased in size. So I can say that the innermost triangle and the outermost triangle are also similar. So what we can see is, let me call this as 1, this as 2, and this as 3. I have seen that 1 is similar to 3. 1 was similar to 2. Also 2 and 3 are similar. since 3 is nothing but a larger image of this triangle 2, so 2 and 3 are also similar. Also what I had seen that the smallest triangle and the largest triangle were also similar. So if 1 is similar to 2 and 2 is similar to 3, what I can say is that 1 is similar to 3. So remember that in similarity all we are concerned is with the same shape, size can vary. And if 1 is similar to 2 and 2 is similar to 3, then the first and the third are also similar.